We study C27, Hamilton's least action principle. Number one, explain why the Euler-Lagrange equation is more convenient than Newton's equation of motion. First of all, Newton's equation of motion F equals ma is F equals time derivative of linear momentum. It is consists of three equations because it is a vector equation. While this F equals ma is has been shown to be equivalent to Euler-Lagrange equation by Euler and Lagrange. The final stage of these equations are equivalent. However, in the beginning, the starting point of Euler-Lagrange equation is a scalar called Lagrangian, that is kinetic energy T subtracted by the potential energy. So dealing with the scalar quantity is much easier than dealing with the vector quantities that has the three components. In addition, if there are many particles, n particles, there are free and generalized coordinates. For example, each particle moving in a three-dimensional space requires the three Cartesian components, and if we have n particles, we have three n Cartesian components. The number of particles becomes very large. The number of equations grows very fast. So the Newton's equation F equals ma should be written in the form for the particles identifier I runs from 1 to n, and the Cartesian component identifier j is a vector index running from 1 to 3. On the other hand, the Lagrangian is additive quantity because energies are additive quantities. The Lagrangian of a system of n particles should be expressed in terms of the kinetic energy, that is the algebraic sum of kinetic energies of n particles. By the way, we need to find the potential energy of n particles if they interact uh, in a non-trivial way. So that depends on the problem itself. The kinetic energy T is algebraic sum, as I told you already. The potential energy should be obtained based on the interaction among particles. The Euler-Lagrange equation that derives from the Hamilton's least action principle to minimize the action that is shown to be equivalent to this Newton's equation. As I already told you, the number of equations at the final stage must be the same, but at the beginning, it only deals with a single Lagrangian. Number two, we consider a curve on the tx plane that connects 2 points. 0, 0 is chosen to be A and B is A comma B. We find the trajectory connecting A and B that are fixed, on which the time elapsed for the travel is minimized. So we first allow arbitrary path running from A to B. Express the length S of x of the path as a functional of x. So x is the trajectory along the time-dependent path. The length of the path is the sum of infinitesimally short straight path of the length. So as ds is the square root of dt and dx. Okay, we have dt and we have a triangle dt and dx, and this is a ds, and this ds is to be integrated to find the total length of this path. If I factor this dt out, then the inside the square root is simplified as a 1 plus time derivative of position x. So square root 1 plus x dot square dt is to be integrated. So x dot is dx over dt, and we call this one to be an action. Action is an integral of something, and we use the path length from the initial to final position, and in between the path is treated to be arbitrary. And for any function, we can compute this path length. So what we're interested in is how to find the shortest path represented by function x of t. In general, the Lagrangian, this is called the Lagrangian. Not exactly Lagrangian, but if we study the Newtonian mechanics, we'll introduce a similar structure. Lagrangian is a function of this path and this position and velocity. Okay, so this Lagrangian in the temporarily, we call it generalized Lagrangian. It is nothing to do with classical mechanics, but it's a geometry. Finding out the shortest path, that is called the geodesic. Lagrangian is function of x and x dot. In this problem, to find out the arc length, it is a square root of 1 plus x dot squared. Find the variation of the integrand. This is the integrand. Variation of the integrand from x of t. This is a certain path, and we'd like to deform this path by a small amount. This is x of t, and we have another function x of t plus delta x of t. So why don't we write it as the x plus delta of the t? So this is a certain path, and this is a modified path by a slight amount. Because Lagrangian is function of x and x dot, we can vary infinitesimally, not at a single point, but it's a whole function. So why don't we write it in as just like the finding out the total derivative of a function, but it is depending on this variation of a function. So Lagrangian's partial derivative with respect to x, and using chain rule, that with respect to x dot, we add them up, and we assume this modification is very tiny, and we can treat this one in the high order approximation. So we can neglect this term, the order delta x squared or higher. By the way, because x of t and delta x of t is completely determined exactly, the time derivative of this delta x, that is a shift of the original path, can be expressed as this. So the notation I introduced, the delta x dot, is identical, by definition, identical to the time derivative of variation delta. As a result, the Lagrangian's variation can be expressed as, we can rewrite this one can be expressed using, if we use Leibniz rule, total derivative and subtract the other term that is applied to the left-hand side, and without derivative, this delta x. As a result, this term can be expressed as this difference. So we have a total time derivative of this, and then we have a contribution proportional to a delta x. Okay, find the constraint of L that makes the functional minimum. Okay, so we obtained this part. So why don't we substitute this one? So we'd like to find out the change in the functional. That functional is the length of the path and from the original path. So we'd like to estimate the difference of the path length depending on the slight shift from the original one. And that was available by changing the make a differential of the integrand from the original value, and that was estimated to be the delta L, and we reorganized the linear combination of delta x and delta x dot as a delta x dependent part and the total time derivative. Finally, we substitute this guy in here, and still we have this delta x squared dependent contribution that are suppressed. And then we have this one proportional to the variation, and the other term is the total time derivative, so we can integrate out explicitly. So this is a trivial because when we compute the length of the path, we do not change the initial and final position. So if we shift these two initial and final position, there is no way to estimate the length. The definition of the initial and final should be fixed to compare the distance of travel along a path and uh, another path with a small variation. Therefore, after integration, the variation of the path at the two end initial and final, these variation must be zero at the initial and final position. Therefore, it is zero. As a result, we would like to find it. And this is another small contribution. And if it is the maximum value at a certain path called x, then the variation does not give anything. If it is a minimum variation by positive delta or negative delta, it should the value of action must increase. That means its first order derivative must be zero. That means this part must be zero to make this the variation of the action, that is the path length, should be the minimum value along the path, a certain path x. Therefore, this is the Euler-Lagrange equation. So if we apply this method to evaluate the variation of the arc length, we first compute the derivative with respect to x. It is an explicit function of x dot, so it is zero. Derivative of x dot is, we can take the derivative, so square root of x prime is 1 over 2 square root of x, and we have this square. So using chain rule, we find the numerator is 2x dot, and this, if it is x dot, it is like that. Therefore, we have final result for the partial derivative of the Lagrangian with respect to x dot is like that. Applying the Euler-Lagrange equation, substitute this one in here. What we obtain is, because this x derivative is vanishing, is a 0. So this one shows that derivative is a 0 means that this one is a constant. If it is a constant, then x dot is a constant. X dot is the time derivative of x. So it is constant. That means from here to there, from A to B, the slope, this is the slope. And this slope must be a constant. That means it is a straight line. So in a Euclidean space, any the path that connects the 2 points with the minimum length, distance of travel, is just a straight line. So this is a very interesting derivation of the geodesic, that is the shortest path. The action of a particle in reality is kinetic energy subtracted by the potential energy. So we would like to apply Euler-Lagrange equation to find out, to show this that is equivalent to the Newton's equations of motion. We have 3 components of a vector, position vector for a particle. We've computed the variation of the action, and we use the same method instead. In previous computation of path length, we have a single variable x. However, we have a position vector that has 3 Cartesian components. So everything is the same except that we have a summation over vector indices I that runs from 1 to 3. The variation of action is also the sum of these 3 Cartesian components' contributions. Again, the total time derivative, it will be subtracted and pulled out, and we have a form of Euler-Lagrange equation style. And we have a single term in the previous calculation for the path length. We have some of x, y, z components. By the way, this delta S must be a 0 if S is minimum, at which the S is minimum for any choice of variation independently of Cartesian components. We have everything should be 0. Therefore, the x, y, z, all of the components must satisfy the similar style of equation. So we would like to see whether it is reproducing the Newton's equation of motion F equals ma or not. First, we consider the cyclic coordinate if Lagrangian L is independent coordinate, then we have a very interesting result. For example, that is a momentum, conservation of momentum. Let's see. X, Y, Z, I have just a 2-dimensional case, so 2-dimensional. So we don't need x3. X1 and x2 are this. So why don't we introduce a generalized coordinate that is called, the first coordinate is radius and the second coordinate is angle theta. Then velocity squared is, we know, r dot squared, radial velocity, and tangential velocity squared. We just replace this one with q1 and q2. So r is q1 and q2 is theta. So we have a q2 dot squared, and this is a q1 squared. The kinetic energy is this, and in our case, 1/2 m x dot squared, that is to be replaced with this. And the the interaction between them is assumed to be the gravitational force. For example, in that case, it is independent, it is depending on q1, that is the radius, and it is independent of theta. As a result, the Lagrangian is kinetic energy subtracted by potential energy, and this potential energy is independent of coordinate q2, that is theta. So it is apparent that q2 is missing in the whole expression. So we'd like to compute the partial derivative of Lagrangian with respect to q2, then this is exactly zero. Because there is no q2 appearing in the Lagrangian. As a result, the Euler-Lagrange equation of this will be definitely this, and the first one is q1 Lagrangian total time derivative and q1 dot. These two are the Euler-Lagrange equation, and this one we have q2 equals theta, and that is independent. Lagrangian is independent of q2, so this is vanishing. And what we find is this. By the way, this one is nothing but the momentum. And what is the momentum? Conjugate momentum relative to this coordinate q2. And means the time derivative of this conjugate momentum of q2 is zero. That means that momentum is conserved. And actually, this is a kind of gravitational force. And if the gravitational force is depending on the radius distance between them only and is independent of angle, then angular variables correspond. The angular momentum is the conjugate momentum relative to this coordinate theta, and that is conserved. There's angular momentum conservation, and it is closely related to the fact that Kepler's second law, that area velocity conservation. Okay, that's it for today. Thank you.